Introduction to Nuclear Technology. Chapter 2. Reactors. Essentials of a nuclear reactor. A reactor is, of course, the heart of any nuclear generating system, and the heart of the reactor is the core, set up to sustain a fission chain reaction at the correct level to provide the required power for as long as has been decided between reloads. Unlike a system based on chemical combustion, where fuel is added and combustion products, including any ash, removed continuously, the fuel stays in the reactor for typically 3 years or so, and only heat is removed. The fissile content must therefore not only be adequate for the initial startup, but must be maintained for a very considerable period. Once the system is going, plutonium generated from uranium-238 to some extent offsets consumption of the original uranium-235, but only in part, and in any case it was not available before the nuclear program began. Uranium-235 was the only fissile material to have survived from the formation of the Earth. The whole operation therefore depended on getting enough uranium-235 into a configuration in which fission could be maintained for the required duration. Historical outline. The history of nuclear energy actually started long before the military programs of the 1940s. About 1800 million years ago, natural reactors operated on and off amid uranium deposits at Oklo in what is now West Africa. At that time, the natural uranium-235 content was about 3%, sufficient for natural water percolating through the ore body to provide effective moderation of the neutrons released by fission. However, with a shorter half-life of 704 million years, compared with 4.47 billion for uranium-238, the natural 235 content has now fallen to 0.72% by atoms. At this concentration, the distance between fissile nuclei is too great for enough neutrons to get through ordinary water, so other moderators had to be used in the original military reactors. In those, plutonium production was the sole object, but large amounts of potentially useful heat were a byproduct later harnessed in the Magnox reactors at Sellafield, which despite some misapprehension was incidentally the pre-industrial name of the site. In time, the generation of power became the principal purpose, and economics, rather than military imperatives, became the driving force of development. In the UK, this led to the Advanced Gas-Cooled Reactor, AGR. Meanwhile, in the USA, more compact reactors were developed for submarine propulsion and evolved into the types now commercially dominant, while Canada went its own way with the CANDU type, also adopted by India. With the fissile isotope of uranium forming so small a proportion, the only ways to achieve a self-sustaining fission chain are to increase that proportion by separating off much of the uranium-238, or use a less neutron-absorbing moderator. Ways of separating isotopes do exist, but are difficult, expensive, and, more importantly in a time of military urgency, slow. Early reactor designers therefore looked to better moderators. The purpose of a moderator is to absorb most of the energy from neutrons liberated by fission. Energy transfer between colliding particles is most effective when they are similar in mass, since otherwise one simply bounces off the other. Protons, as in water, are an ideal match in mass for neutrons, but have an inconvenient tendency to absorb them instead. The second isotope of hydrogen, deuterium, is the next best match with very little absorptive tendency, but at only 150 parts per million of hydrogen needs slow and expensive isotopic separation. Another possibility is graphite, a form of carbon, which with an atomic weight of 12 is a relatively poor match but cheap and abundant. Britain chose graphite, Canada heavy water, deuterium oxide. Eventually isotopic enrichment of uranium developed enough for the USA to develop its remarkably successful range of reactors moderated by ordinary light water. A power reactor must not only provide the conditions for a vigorous self-sustained nuclear chain reaction, but also control its rate at the required power level, deliver the heat to an electrical generator, prevent the escape of radioactive materials, and prevent undue irradiation of operators or the public. Essential components. A reactor essentially comprises fuel, with which is included its immediate containment and structural elements, which can be substantial and complex, moderator, coolant to carry the generated heat to an electrical generating system much the same as in any other power station, a control system to hold the reaction at the required rate, shielding to prevent the escape of radiation, and an outer containment for weather protection and as a barrier in case of leaks. Various types used for power generation are commonly known by acronyms. LWRs, light water reactors, with ordinary water as both coolant and moderator, include PWRs, VVERs in Russia, pressurized in the primary circuit to prevent boiling, raising steam in a secondary circuit to feed the boilers, and BWRs, boiling water reactors, in which the primary coolant is allowed to boil and drive the turbines directly. Then there are CANDOs, moderated by heavy water, pressurized and again raising steam in a secondary circuit of ordinary water. Magnox and AGR, British designs with graphite moderator and carbon dioxide coolant. RBMK, a Russian design with moderation provided by the boiling water coolant. HTR, various high temperature designs for good thermodynamic efficiency, using fuel composed of sub-millimeter particles individually coated to contain fission products, then compacted with graphite into blocks, or, in the pebble bed variant, 6 centimeter balls. A disadvantage of all these reactors is that they realize only a part, generally about 1% or less, of the energy theoretically obtainable from their heavy element content. This is because the slow neutrons, best for fission of fissile nuclei, cannot induce it in uranium-238 or the even-numbered isotopes of plutonium. For this, high-energy neutrons are needed. Hence the FR fast neutron reactor with no moderator and currently molten sodium as coolant. Considering the various essential components of a power reactor system in turn, the fuel usually comprises uranium oxide as pellets about 1 centimeter long, packed into tubes of a zirconium alloy or sometimes stainless steel, themselves assembled for ease of handling into clusters of up to several hundred. Magnox is an exception, being uranium metal as massive bars encased in slightly alloyed magnesium. As a rule, the UT35 content is enriched to a few percent. Sometimes plutonium is used instead to enhance fissile content, and this practice will probably increase. Again, Magnox was originally an exception, using natural uranium, as did Candu at a time of limited access to enrichment, though more recently some enrichment has been applied to permit longer residence. Sometimes burnable poisons are included. These are materials that absorb neutrons strongly, but in doing so are converted to poor absorbers, so slowing the decline of reactivity. Fertile nuclides. Also helping to flatten the decline is the conversion of fertile to fissile nuclei, such as uranium-238 to plutonium, or an even to an odd-numbered isotope of plutonium. In a reactor fueled initially with uranium, plutonium may eventually provide about 30% of the power. In that case, plutonium only partly replaces the uranium-235 consumed. In other circumstances, there may be a net production of fissile from fertile material. Breeding. For this to occur requires at least 2 neutrons per fission, beyond those lost to the system or absorbed unproductively within it. One to replace the nucleus destroyed in that fission, another to cause the next in the chain reaction. In the uranium-plutonium cycle, this is possible only in a fast neutron flux, since with thermal neutrons the neutron yield is smaller and absorption stronger. The moderator. This has already been discussed, but to recapitulate it must be composed largely of light atoms, a poor absorber of neutrons, and preferably inexpensive. Of the light elements used, hydrogen is cheap and has the best possible mass match, but absorbs some of the neutron flux. Deuterium has the next best mass match and extremely low neutron absorption, but is expensive to separate from the predominant lighter isotope. Heavy water can represent about a quarter of the capital outlay for a Candu reactor. Carbon is cheap and again has very low neutron absorption, but a much poorer mass match. For that reason, many more collisions are needed to bring down the neutron energy, taking long flight paths, so that the core is necessarily large physically. Most commercial reactors now use ordinary light water as both moderator and coolant. The coolant must be a mobile fluid, whether liquid or gas, readily available, stable to heat and radiation, unreactive with the fuel cladding, and in case of damage with the active substance itself, and a good heat transfer medium. Of those available, water is cheap, familiar, can also serve as a moderator, but is somewhat corrosive. Carbon dioxide is cheap, but reactive at high temperatures, and in pure form can gradually erode a graphite moderator. Helium has good flow properties and is chemically unreactive, but relatively expensive. Molten sodium provides excellent heat transfer, has flow properties similar to water, does not need to be pressurized to prevent boiling, but is very reactive chemically, especially with water, and is used only in fast reactors. Molten lead is stable with low absorption, but corrosive towards steel. It is also rather inconveniently high melting, unless alloyed with bismuth, which raises issues of activation. Control considerations. Control is a crucial issue with nuclear reactors. Even thermal neutrons move at thousands of meters per second, and successive events in a fission chain follow on a millisecond timescale, far too fast for mechanical intervention to be effective. Control therefore demands instant automatic responses to any departure from the desired power level. This can come about only through negative feedback inherent in the system, whereby any such departure itself brings about a corrective response. For action on a longer time scale, such as load following or shutdown, neutron absorbing rods are mechanically inserted or withdrawn. Their effectiveness depends on a slight delay in the release of some neutrons, allowing time for intervention. Feedback mechanisms. The situation in a fissioning system is never absolutely fixed, as the somewhat random nature of nuclear events implies constant slight fluctuations in power level. Negative feedback requires that any such fluctuation should itself generate a response in the opposite sense. This depends on complex interactions between different effects. Fuel temperature. The fission cross-section declines with rising temperature, so long as resonances do not become more important, which to that extent is instantly self-correcting. However, the absorption of non-initiating neutrons also declines. A rise in moderated temperature rather more slowly reduces the effectiveness of inducing fission, as there is a slight time lag. Loss or boiling of moderator reduces both the effectiveness of moderation and the extent of any absorption. A conflict usually, but not always, resolved favourably. Finally, poisoning effects can be a serious complication, notably with xenon-135. Xenon poisoning. This results from the decay of iodine-135. Xenon-135, the decay product, has an exceptionally high absorption cross-section, but in absorbing a neutron is converted to xenon-136 with practically none. In the normal operation of a reactor, the 135 level is thus kept very low. However, if the reactor is shut down, the isotope builds up. Restarting before it has sufficiently decayed is therefore very difficult, but if successful, would progressively destroy the poison, introducing a very strong element of positive feedback that might lead to runaway reaction. For that reason, any shutdown of more than a few minutes duration must be prolonged to at least several days to allow natural decay to cesium-135. Reduction to 0.1% of peak level would take about a fortnight. Adverse feedback. The classic example is the Chernobyl accident of 1986. The RBMK type of reactor is moderated primarily by graphite and cooled by boiling ordinary water, which does contribute to moderation, but more importantly absorbs neutrons. To an extent depending on the enrichment of the fuel, a loss of coolant through excess boiling can reduce absorption more than moderation, so that reactivity increases and boiling is accelerated. Positive feedback. The accident started in a test of whether the momentum of the electric generators could supply enough power to maintain essential cooling until emergency supplies kicked in. The reactor had already been operated for some time at a very low power level, and in attempts to raise it, ill-trained operators progressively flouted the standing instructions and disabled the safety systems. When they eventually succeeded, positive feedback through both poisoning and coolant void mechanisms took over. Power rose uncontrollably to an estimated 100 times the normal maximum. The core was heated to incandescence. A steam explosion blew off the lid of the reactor vessel and was followed by a second explosion, probably of hydrogen generated by a reaction of steam with the zirconium cladding of the fuel. Exposed to air, the grossly overheated graphite moderator burned, sending a plume of debris high into the atmosphere. It is important to recognize that the very possibility of such an accident was due to the peculiarities of the RBMK design, and no other reactor type could have behaved in a similar manner. The following slides deal with various kinds. Magnox reactor. Please note that the drawings in these slides are strictly schematic, showing merely the arrangement and connections of the different units. They bear very little resemblance to the actual structures. Magnox reactors are named after the magnesium alloy in which the uranium fuel is encased, have a graphite core with channels containing the fuel rods. Carbon dioxide coolant passes through these channels to heat exchangers, where steam is raised to drive the generators. Neutron-absorbing control rods operate within other channels. The relatively low operating temperature dictated by the limitations of the metal fuel mean that thermodynamic efficiency is rather poor. Advanced gas-cooled reactor, UK only. To overcome this drawback, and to reduce the physical size of core needed for criticality, the Advanced Gas-Cooled Reactor, AGR, uses enriched uranium oxide fuel encased in stainless steel. Carbon dioxide again serves as coolant. Pressurized water reactor. PWRs, developed from necessarily compact designs for submarine propulsion, again use enriched uranium oxide, but clad in a zirconium alloy with very low neutron absorption. The light water coolant is pressurized to prevent boiling, but a pressurizer in a separate chamber maintains a steam space to provide some flexibility. The water tends to pick up some radioactive content from damaged or corroded fuel elements, and to prevent contamination of the generating equipment, steam is raised in a secondary circuit. The boiling water reactor, BWR, is rather similar, except that the primary coolant is allowed to boil and to drive the turbines directly. It thus saves the cost of the heat exchangers, which tend to have trouble with the welds of the tubes, but complicates maintenance of the somewhat contaminated turbines and condensers. Because of the steam separator above the reactor to remove drops of water, control rods are inserted from below. CANDO is similar in principle to the PWR, but horizontal fuel channels are contained within individual pressure tubes, and so refueling is possible on line. The heavy water coolant is an efficient moderator with particularly low neutron absorption, so natural uranium fuel can be used. Although originating in Canada, the principle has been adopted by India with some further development of its own. The pebble bed reactor is a variant of the HCR type, in which balls of fuel are passed through a chamber surrounded by a graphite reflecting moderator. The balls are monitored for fissile content at the outlet, and either returned if still good, or sent to waste. The form of construction, with individual particles coated successively with pyrolytic carbon, silicon carbide, and another layer of carbon before being compacted with graphite, is particularly robust against leakage of fission products, and exhausted pebbles are themselves an excellent waste form. Control rods cannot be operated within the fuel bed, and so are housed within the reflector. Their range of influence is limited, and such reactors are intended to serve as relatively small units of about 100 megawatts capacity. Finally, we come to fast reactors, sometimes known as fast breeder reactors, although it is the neutron flux rather than the breeding that is fast. And in fact, the objective may not necessarily be breeding at all. Their original purpose, at a time when a shortage of uranium was expected, was, however, to generate more fissile material from the otherwise almost useless depleted or recovered uranium available from the thermal reactor program. A relatively small core of uranium and plutonium oxides is surrounded by a blanket of depleted uranium. The small size means a high density of energy generation, consequently a high temperature, and to take the heat away efficiently, molten sodium is used as primary and secondary coolant. Being below its boiling point, it has no need of pressurization. The point of the intermediate sodium loop is to prevent any risk of radioactively contaminated sodium reacting with water through a leak in the steam generator. It turns out that such leaks, generally started by corrosion on the water side, tend to be self-plugging. There have been suggestions that the intermediate loop might be safely omitted with a very significant saving in cost. For political or economic reasons besides the continuing availability of fresh uranium, interest in fast reactors declined in Britain and France, although it continues in Russia and Japan. Thermal versus fast reactors. A particular feature of thermal reactors is their remarkable safety record. Even at Chernobyl, the accident was the result of gross malpractice on a reactor of uniquely unstable design, while most of the casualties were the result of mismanagement in the aftermath, with attempts to conceal the event for political reasons. The great drawback of such reactors is their inability to extract more than about 1% of the energy theoretically available. And since uranium mining is the greatest environmentally damaging part of the cycle, there is a moral argument against discarding 99% of the product when it could be used constructively. Moreover, while at present there is no shortage of uranium, the supply is finite, and failing a viable alternative, such profligacy is liable to become unsustainable. Fast reactors capable of using this material do arouse some concerns on safety. The fuel configuration, unlike those in a thermal reactor, is not the most reactive possible, while the sodium coolant, although operating some 200 degrees below its boiling point and so needing no pressurization, has a positive void coefficient. That is, its loss could raise reactivity. On the other hand, a fast neutron flux is the only means of destroying plutonium generated in the thermal cycle and a source of anxiety on security grounds. Other coolants are being considered. Summary. Despite the wide variety of reactor types proposed at one time or another, very few have been generally successful, with LWRs, whether pressurized or boiling, predominant. Ability to make further use of fuel discharge from them is raising interest in CANDUs, which are already important in India. The need for fast reactors has been postponed, and they may well be first adopted as plutonium burners to ease a perceived storage problem. Novel types may, however, be introduced earlier for special purposes.